Hello community! Last time I showed you that we have a look at the tokenizers and how we build our vocabulary based on a very specific domain knowledge. Now, in the second video now, we have converted our human sentences from the human language now into a number, a vector, a tensor, a high-dimensional representation of a vector space. So now we're here, which natural language processing model now to choose? Currently, and I really mean currently, in December 2022, we're looking at transformer-based models. Now, if you want to learn a little bit about transformers, I have here a video for you. It's called A Beginner's Guide to Transformers. This is the link. I leave you the link in the description of this video. And transformers operate with a specific mechanism. And this is called self-attention. And this is a beautiful mechanism that was developed over years. And if you want to understand multi-head self-attention of transformers, let's say, for example, a BERT architecture, I have a specific video explaining this to you. But this takes half an hour, so it's out of the scope of this video. But if you're interested, have a look at those two videos. Now, having talked to you about BERT, a transformer structure, BERT was more or less invented for a word representation. And it didn't took long, and people came up with something called a sentence transformer. So now we take all the words in a sentence, we build now a mathematical object representation of all the words in a sentence, and a sentence now is the object that becomes a vector embedding object. So we have now a vector representation of a sentence. This is here in this particular video where I tell you SBERT sentence transformer is not a BERT sentence vector. BERT is more or less just a bidirectional encoder stack explained in detail here in this YouTube video of mine. It is an introduction, a tutorial to sentence transformer. And if you want to see how those sentence transformers are placed within the world of artificial intelligence, I have here a 1-minute video giving you a rough idea operating in a knowledge space, in a vector space where we store our knowledge. Beautiful. These are the recommendations. Now, to show you that you get a feeling, I'll give you a little bit of a code and I'll show you the result of this code. So this is here, if we do some coding in a Jupyter notebook, we have PyTorch or PyGeometric or whatever you like, or TensorFlow you can use. Just to show you, you have a sentence 1. This sentence has to be a text piece because actually it consists of 2 sentences. And the text piece 2 consists also of 2 sentences where there's also a question part of it. And you say, so this is my human sentences, my 4 sentences. How can I convert this to a mathematical representation? Now, there is something done for you. This is called a TF-IDF vector. You just put in the thing. You say, hey, do the extraction for me. And what you get out is what we call a feature extraction with a vectorizer. So it vectorizes our human text. And what you get out is for each word here, and notice this TF-IDF is a statistical representation. This is not what we use in artificial intelligence where we have a knowledge. This is just pure statistics. That's it. Just to show you this is a beginning. So what they do is they say, hey, I have those words in these 4 sentences, I have those dominant words. And those words here for sentence 1, you see Christmas is not part in the first sentence. So first text is, this is a good job, it will not have anything than quantum. Christmas is not here. But in the second text sentence, we have Christmas and it gets a value. So you see, if you look now at this as a row of a tensor, of a matrix, you see how you can go from human sentences to numerical representations. It is that easy. So for each piece of text or each sentence or whatever, if you have a paragraph, you even can, for a scientific publication that has 20 pages, you can construct a vector. This is done. This is just statistics. So there's a specific video where I show you that you don't only have the term frequency approach, that is a pure numerical statistic approach, but we can go for a learning approach where we really take care about the position of words in a sentence and we have this semantic context. And this is the power of the transformer network, for example, BERT. We use PyTorch, and if you want to have both examples in code, there's this video for you, and here the HTTPS link. You can have a look at this, takes about 40 minutes, 45 minutes, but there's a lot of mathematics involved, just to give you an idea. And going now from the statistical approach to a sentence transformer approach, this is also a piece of code, and I'll show you the result in a PyTorch tensor. It is the same. We just say, hey, we take now a sentence transformer model based on a BERT model. We have those self-attention mechanism working for us. We take a specific model that has been pre-trained on hundreds of GPUs for weeks or maybe months. And the amount of text it has been trained is, I don't know, all of Wikipedia, all of the English literature and all books and all, I don't know. It's amazing the amount of text you can train on. This is a pre-trained model. What is the meaning of this? Well, simply, it just learns English. So this is a pre-trained model that gives you a good English understanding with a medium level of semantic understanding. And this is available freely on the internet, on a Hugging Face server. This connects automatically in the internet to Hugging Face, downloads these models between 3 and 10 and 20 gigabyte files, downloads it, and we have those models available for us. And then I can encode my sentence. And as you can see here, I'm working here with a movie data set. So I have 9,700 movie titles. And I encode each movie title, you see, one row here with 400 vector coordinates if you want. This is a 400-dimensional representation of the first human movie title. This is a tensor and all 9,000 rows we have here. So you see, this is it what we are talking about. This is what you're operating with if you transfer human text to machine code. This is the way you operate it, and you have to have the mathematical understanding what operations you can do in your space with your tensor element. Now, sentence transformer in itself a really complex topic, and I have a whole playlist on them. I have, I think, close to 50 videos. So this is my YouTube playlist. If you want to find it, this is the title of the YouTube playlist, the bioencoder transformer model. And I show you here how you can use it on documents, how you can learn it, how you can use it with frozen layers, how you can include new knowledge to it, how you can transfer domain knowledge. Let's say you learned something about biology, and now you want to load up all the medical knowledge. You have to transfer domain knowledge from medicine to your already chemical model or medical model or whatever model you have. You have domain adaptation. You can do amazing things. For here, for example, I took the IPCC report, the whole document, and I showed you how to visualize the content of all, I don't know, 100,000, 200,000 sentences of this document. So you can have a semantic cluster structure and how those topic clusters are related to each other. And we start then here to move into the area of a graph representation. And we can also do learning on a graph structure. But for the moment, we are here on a linear structure. We are here operating, as I showed you, on a linear structure. And a linear structure is a sentence. Now, if you say the next more complex thing, of course, is an image, because an image has an X and a Y axis. So you have, let's say, a 16:9 image, and you just take read every row. And if you have this grid, you have objects called convolutional networks, where you have a kernel, a filter operation going on. Or if you go even to higher abstract objects, this is where we enter then the graph domain, where you have just relations between objects in a particular, let's call it topological, very general topological space. Now, if you are so brave and you made it till here, I have some bonus material for you. If you want to understand transformer, I told you there's this video, have a look at this. But just to show you, this is it. This is an encoder stack that works bidirectional. This is it. There's nothing more to it. It's easy. Here at the bottom we have an input, a sentence. And you see here we have a sentence, how are you, question mark. Beautiful. This is it. Nothing more to it. You have some start tags, some end tags. You have a tag between sentences, between punctuation, for example. And you have then a numerical representation. This is what I showed you in the first video. And then all of this here, this stack of encoders. Now every little dark blue encoder has this self-attention mechanism and a feed-forward functionality. This is explained in my other video. But just to show you, for each word, you do encode in, encode out, encode in, encode out, and you get a better mathematical representation of the word in relation to all the other words. And then the output of BERT, this encoder stack, is simply an embedding of a contextualized word. And contextualize is important because we take into consideration the whole sentence, what the whole sentence means. And if we have words that are not absolutely clear in itself, given its surrounding and the way the words are used, you know what is the meaning of those words. So those contextualize mathematical embedding, and we get an embedding is, for example, a vector representation, and you have then a new vector taking into consideration the syntax and the semantic of the sentence. Now, if you want to learn more about sentence transformers, about models, about a little bit more about mathematics, this is a here video I recommend to you, and to show you what it is all about. Sentence transformers, they use not just one neural network, but they use a specific class of neural network that contains two identical networks. Now the power is here you have the same configuration, so it's rather fast, and you have the same weights. So two networks are connected below the surface and share the same weights. And the parameter updated is mirrored across both networks. And we call these a Siamese neural network, a twin neural network with similar inputs, and we get feature vectors. And if you want to have a visualization, here we are. We have now the problem, are two sentences similar, but not just similar in the words, but similar in the meaning of the sentence. All the words together is the meaning of a sentence which has complete different words in sentence 1 and complete different words in sentence 2. Does it have the same meaning? Does it refer to the same topic? And the way you do this is with this twin architecture structure, where you again have those BERT element, but not just as one element. Then you have a specific tokenization that's going on. You then have to sum up about all the different output of all the different layers. There are a lot of possibilities. And you can put the maximum over the time of all outputs. You can work with time series, whatever. But the interesting thing is that these pooling layers achieves a fixed size sentence embedding, a fixed size vector representation. Let's say we have 368 dimensional vector that is encoding the meaning of this sentence. In a mathematical way, you cannot read anymore. But the nice thing is The other sentences you can compare. If you have 1 million sentences, you can compare each sentence to each sentence. And you can then find a vector representation for each sentence in relation to the other sentences of your document, of your body of knowledge, of your domain knowledge. And then you can have a simple mathematical operation of a cosine similarity. You can calculate the closeness of vectors. And the sentences are mapped in the vector space such that the sentences with similar meanings are close in a vector space. And the meaning of closeness is mathematically not trivial. So we use here a lot of mathematics to understand when is the meaning of two sentences similar, given that all the words may be different. And this is the beauty of artificial intelligence. With pure statistics, you would never come to this result. So we need to learn a lot of sentences. We have to have millions and millions and millions of sentences that we learn. And then when we are given new text, we, from our learned knowledge, like a child that learns for 10 years, suddenly we say, I understand this in this sentence refer to the same topic or subjects. So you see, it is beautiful. And this is also the transformation of a sentence in a human language, let's say English, in a specific region with a specific environmental condition, with a specific economy referring to real-world objects, politics, news, whatever, physics. And we get a vector representation that is specific to the field of the sentence. So you can have all the sentences of CNN or Fox News or whatever is your broadcasting station. You take 100 million sentences, what they say, and you can compare it to other sentences. And what you can do, you can have a clustering of topics, a clustering of themes that they address. You can have a cluster of argumentations that they provide. And suddenly you see the connectivity of 100 million sentences. And maybe it's just 2 or 3 main axes that they argue. So this is a very powerful instrument that we use. And another, I think the most advanced version, I have here a video on code neural information retrieval. So this is not a lexical retrieval. This takes care about all of this, what I just told you about sentence transformer, this pre-trained knowledge applied to your domain knowledge. You can code, and I showed you in this video, we code a semantic neural information retrieval system. For example, you're a huge corporation operating globally. You have a lot of documents, 10 million, 100 million documents. You have millions of sentences describing your customer experiences, all your process description, your in-house knowledge, your patents, your trade secrets, your main partners, your ideas about strategy, expansion, whatever. You don't want to have this open where everybody can experiment with it. So you can build with your own sentences, your own semantic neural closed secure information retrieval system for your specific company requirements. So you can do a search about all the different topics, about different countries. It is far beyond what you can do with SAP, what you can do with database, because this is to a level that it analyzes the semantic neural information of your documents. So I hope to have ignited a little bit of interest. And this is the end of the video. I hope you enjoyed it, and I see you in the next one.